Okay, in this video what we're going to be doing is we're going to go over how you hear, and the structure we're going to focus on in the inner ear is the cochlea. So remember, talking about the inner ear, we had the areas that were concerned with equilibrium or perception of equilibrium and balance. This is going to be the semicircular canals, the vestibule shown here, and then part of the inner ear that's concerned with the mechanism of hearing is the cochlea. And the cochlea means snail shell. It's wrapped around and around like a snail shell. And this is where we're going to be focusing in on. Well, if I were to take a section through the cochlea and look at it inside, it would look like this here. And so when you take the cochlea and you slice through it, you would look at something like this. And you'd see that it's subdivided into 3 channels that spiral around a bony core. So the bony core is here, and here are the 3 channels. The partitions that separate the 3 channels are shaped like the letter Y. So this would be the stem of the Y, and then it comes up. Here's one of the arms of the Y, and here's the other arm of the Y. I give you the 3 channels. The one in the center here, which would be the center of this Y, is the cochlear duct, and it contains a fluid called endolymph. Within this cochlear duct, we're going to see that there's little tiny hair cells here that when the hairs bend, it sends action potentials to let the brain know what specific tone or frequency you're listening to. Above it, we have what's called the scala vestibuli, which contains perilymph. And below it, we have the scala tympani, which also contains perilymph. And we're going to see that these 2 chambers are actually connected to each other. So the cochlear duct, scala media, is this right here. It lies between the wings of the Y. It's composed of membranous labyrinth. So when you're looking at the inner ear here and the cochlea, this structure here is the membranous labyrinth, and that is here. Now around this membranous labyrinth, we have the perilymph, which is found in the scala vestibuli and scala tympani, and that would be around this area. So the cochlear duct contains endolymph, and it has this organ of Corti, or spiral organ, and this is going to have the hair cells that sit on top of this basilar membrane right here. The vestibular membrane comes up this way, and that keeps this chamber separate from the scala vestibuli and scala tympani. The cochlear duct is separated from the scala vestibuli by this vestibular membrane, and it's separated from the scala tympani down here by the basilar membrane. The scala vestibuli is a channel that lies above the cochlear duct, and it contains perilymph. The scala tympani shown down here is a channel that lies below the cochlear duct and also contains perilymph. These 2 channels are connected to each other by a structure called the helicotrema. So shown here, when sound waves beat on the or cause the tympanic membrane to vibrate, it sends the vibrations through these auditory ossicles, and the stapes, which is in contact with this oval window, moves back and forth to set pressure waves that move through the perilymph up here. So this top channel is a scala vestibuli. Well, the scala vestibuli goes all around the cochlear duct, and when it gets to the very end here at the helicotrema, it becomes a scala tympani, which comes around, and that's right in back of the round window. So as you push on this fluid, the pressure pushes all the way around to here, and this causes the round window to protrude slightly. So these 2 chambers shown here, the scala vestibuli and scala tympani, are actually connected via this helicotrema. If they weren't connected, and if this was just solid bone at the round window, you wouldn't be able to push this fluid very far in at all, because fluid's not very compressible, at least water's not very compressible. So having this window, this round window, and them connected like this allows pressure waves to go through. And depending on the frequency of those pressure waves, we're going to see that it moves this basilar membrane up and down, and the hair cells that are on this basilar membrane will bend as they contact what's called the tectoral membrane. So different frequencies of sound will cause this basilar membrane to move up and down. High frequency sounds are going to cause the basilar membrane to move up and down close to the oval window, whereas low frequency sounds are going to cause the basilar membrane to move up and down further away from the oval window. And we'll get into the mechanism by which we hear in just a few slides. So shown here is a histological structure of the cochlea cut through, and you can see here's the organ of Corti, And then here's your scala tympani here and the scala vestibuli here. And these chambers are all connected, but it spirals around. We're talking about the cochlea. The cochlea is here in the inner ear. Here's another view of the slide that shows the cochlear duct here. The tectoral membrane's bent down, but here's that scala vestibuli, or vestibular membrane, and the scala vestibuli is filled with perilymph. The scala tympani filled with perilymph. Here's the basilar membrane that those hair cells sit on. It's a beautiful structure when you look at it histologically and the way it functions. Shown here are the hair cells, and they're on top of this basilar membrane. And then here's the tectoral membrane, and the hair cells will move up and down, and they get bent as they come into contact with the tectoral membrane. And as they bend, they're going to send action potentials via these sensory neurons into the area of the brain to perceive hearing, your temporal lobe. Here's a slide of this structure. Here's that tectoral membrane. We have the organ of Corti here with the hair cells, supporting cells, hair cells. Organ of Corti, also called the spiral organ. This is the organ for hearing. It lies on the basilar membrane shown here and has about 16,000 hair cells that are the receptors for hearing. So when you look at this, you're going, well, I only see a few. I see 3 here for the outer hair cells and 1 here for the inner hair cells. Well, this is actually going all along that cochlear duct. So if I come back to this slide here, here's going to be the area where you have that cochlear duct. These hair cells are going all along this cochlear duct. So that's how you get 16,000 of them in this long line here. And they'll just go around with the cochlear duct as it spirals around. Now at the basilar end, the hair cells synapse with a cochlear branch of the vestibular cochlear nerve, or auditory nerve. And that's this branch here. When we look at hearing, basically these sound waves as they travel through the air are going to cause air molecules to vibrate, and they travel in what we call waves. So a wave, like you drop a pebble in the water, it sends out these waves across the water. Well, sound wave travels through air in much the same way. When you look at the wave length, this is just from a crest of the wave to the next wave, or you can go trough to trough. And the frequency of sound is based on the size of the wavelength. High frequency sound is going to have shorter wavelengths, whereas low frequency sounds are going to have longer wavelengths. Well, as these different wavelengths come in, they cause a tympanic membrane to vibrate depending on the frequency of the wavelength. And then that's going to cause the auditory ossicles to move back and forth based on that frequency, which is then going to push on this oval window at that particular frequency. And then those frequencies, those sound waves, are going to be transmitted through the perilymph. And as it transmits through that perilymph, here, those different frequencies are going to cause the basilar membrane to move up and down, which is going to cause these hair cells to be in contact with the tectoral membrane, and they're going to bend. And depending on the frequency and what hair cells get bent, that sends signals that you're hearing sounds at this particular frequency. So when you come back here, high frequency sound, for example, if you have the high frequency, ah, that would be a high frequency. It's going to cause the basilar membrane to move up and down closer to the oval window, so these hair cells get bent and they send a signal to your brain that you're listening to a high frequency. Low frequency sounds, they're going to move through and they're going to cause the basilar membrane to be moving up and down further away from the oval window. And when these hair cells bend, they send signals that you're listening to a lower frequency sound. So when we look at the mechanism of hearing, the auricle, outer part of the ear, is going to direct sound waves into the external auditory canal. And this is just for your information. Sound waves travel at a rate of about 768 miles per hour at sea level. Sound strikes the tympanic membrane and causes it to vibrate at the same frequency as the incoming sound waves. The eardrum vibrates slowly in response to low frequency and rapidly in response to high frequency. Oh, I don't have a very good high voice. High frequency. Now, the central area of the eardrum connects to the malleus, and then the malleus is going to vibrate the incus, and the incus is going to vibrate the stapes, and the stapes is going to move in and out of this oval window. So the stapes vibrates against the oval window here, and then that's going to set up fluid pressure waves in the perilymph of the cochlea. So as the oval window bulges inward, it pushes on the perilymph of the scala vestibuli, which is this top chamber here, and these pressure waves are transmitted to the scala tympani and eventually to the round window. Now these pressure waves can move through this organ of Corti here, and they can also move all the way around and vibrate from the backside as well. The round window is going to move out, so those pressure waves move through this cochlea and then they push out on the round window. And they're going to vibrate the various areas of the cochlear or the organ of Corti, cause those hair cells to move up and down to give you the various frequencies. The pressure waves in the endolymph cause a basilar membrane, which is shown here, to move up and down, and that results in the hair cells of this organ of Corti to move against the tectoral membrane. And bending the hairs is transduced into electrical impulses, or those action potentials that are going to travel via this cochlear nerve to the area of the brain involved in interpretation of sound, that temporal lobe. The hair cells of the organ of Corti, they're arranged in rows, and very soft sound can stimulate only a few hair cells in a portion of one row, shown here, whereas loud sounds will stimulate more of these. And you've probably had that where you go in and you listen to a rock concert and you're hearing the music, it's really loud. So when you're looking at loudness of sound, the loudness of sound is determined by the amplitude of the wave or the height of the wave. So I'm going to come back here, and so when you look at amplitude, loudness is by amplitude. Now, the louder the sound, the higher the amplitude, the bigger the wave, and that's going to cause that basilar membrane to move up and down with a greater extremes. Now, as that does that, it's going to cause these hair cells to bend, and a lot of those hair cells are going to get bent. When you're listening to loud music for long periods of time, when you come out of that area and you don't have the loud music any longer, it takes a while to get your hearing back. And the reason why is because these hair cells get tangled up. And it may take a few hours to overnight for them to detangle themselves so you can hear normally again. Over time, if you listen to loud music, chronic loud music, then these hair cells can bend and break, and which would kill these particular type of cells here. And that can result in deafness, specifically certain frequencies you're not going to be able to hear. For example, I'll hear a vehicle come up next to me and they have the bass really loud, so loud that even though my windows are up, their windows are up, I can feel the sound waves come through my car and vibrate against me. Well, those people in that car listening to that over and over again are going to cause their hair cells to bend and possibly get damaged and die, and then they're going to have permanent hearing loss in those particular frequencies where those hair cells were lost. If you listen to high frequency sound, they're detected closer to the oval window. Low frequency sounds are detected further away from the oval window. Now when we come back, we're going to talk about the vestibular apparatus and equilibrium.